Hi, my name is Calvis Rice, and I'm the Director of Business Development at IPS. And today I'm going to be talking about maximizing sellable can output. The number one question that every single can plant has always had, has today, and certainly will have tomorrow is this: how do we get more cans out the door? To have an effective and important conversation about this topic, we need to first talk about what is the maximum that a can line is capable of outputting. So let's take an example line, one that runs 365 days a year without stopping, 24/7. And let's base this line off of a rated speed of 2,400 cans per minute. This line would have a max output of 1.26 billion cans. And we all know this is unachievable, but this at least gives us the ceiling of what is possible. And from this number, we'll start subtracting output. The first area of output loss is due to scheduled maintenance. And a typical can plant will have about 15 days a year where they're down for scheduled maintenance. And these 15 days will have approximately 51.8 million cans associated with it. Now, we call this a loss, but we all know that this is actually an output investment. And here's why. You are going to have maintenance, whether it is scheduled or unscheduled. And scheduled is much more effective. We all intuitively understand this. But scheduled maintenance looks something like this. Everybody has their tools. Everybody's in their places. Everybody knows exactly what to do, so when the can line goes down, the job gets done and the line gets back up to making cans. This is in comparison to unscheduled maintenance, which looks more like this. And no matter how skilled or talented your staff is, unscheduled maintenance will never be as effective or as efficient as scheduled maintenance. So now, let's look at our next area of output loss, which is, of course, non-scheduled downtime. So this is as a result of mechanical breakdowns or electrical breakdowns that cause the entire line to shut down. This is what I call code red emergencies. This is because that line should not go down, and if it does, everybody should be paying attention to how to get that line back up. So let's put some numbers behind this. So let's say that you had non-scheduled downtime for just 2 hours a week. That is only 1% of your potential operating time over the course of that week. That alone will cost you almost 15 million cans a year. So let's put that into perspective. If we take a standard 211-413 can, that is approximately 1,800 pallets of cans. And that could cost you $600,000 or 23 million baht of gross profit. And if I'm going to use numbers, I want to explain where these numbers came from. So this is based on a gross profit per can of about 4 cents. And this is from a cost per can of 6 cents and a sale price of 10 cents. So if your numbers are different, then take that for what it's worth, but I want to share where my numbers came from and what I am talking about today. So let's take those 1,800 pallets of cans on an annual basis that are lost to non-scheduled downtime, and just think about this. Those are gone forever. That opportunity is flushed down the drain. So how do we minimize non-scheduled downtime? The first step is to maximize the effectiveness of your scheduled downtime. So make sure that you have your parts on site, you have your labor scheduled, and there's a game plan. Everybody should know what they're doing to maximize maintenance day effectiveness. Number 2, prepare for code red situations. It's not if, it's when your can line goes down for non-scheduled maintenance. So the worst thing in the world is to go over into your specialty tools section and find a mess or the tool's missing. So make sure your tools are organized and they're ready to deploy when an emergency hits. And thirdly, have a pit crew philosophy. If the line is down, everybody on the floor should know that their number 1, 2, and 3 priority is to get that back online. Get the problem fixed, get the line back to making cans. So the next area of output loss that we'll talk about is decreased performance. This is running below the rated line speed. And this is what I call the silent killer, because the untrained eye could walk the floor and never know that there is a problem. But, for example, at just 50 cans per minute slower than the rated speed, this will end up costing you nearly 25 million cans on an annual basis. Putting that into perspective, that's more than 3,000 pallets of cans worth almost $1 million in the trash, gone forever. So, how do we address decreased performance? First off, never treat machines like spares, especially body makers. Body makers are like F1 race cars. They're $1 million machines, and they should be making cans at all times. And second, never fix issues with Band-Aids. So a problem we often see is a decorator or a knicker tripping out cans at their rated line speed. So operators will decrease the line speed or decrease the machine speed to make sure that the problem goes away. That's a Band-Aid, and that will cost you over time. So fix the issue. The next area of output loss is spoilage. And when we talk about the impact of spoilage, there's actually 3 areas where it will hurt you. This is why I call it the triple disaster. The first area that it'll hurt you is that spoilage actually costs money to make. And that hurts, especially because when you make spoilage, you're also wasting the opportunity to sell that can. And that hurts. And finally, every single can of spoilage wastes resources that are never again regained. If a can turns into spoilage, those resources were used for no reason. So let's talk a bit about the cost of spoilage. So we all understand that the goal of a can line is to convert aluminum into sellable cans. But in the middle of the line, if there's a stop and a can gets kicked out and becomes spoilage, that spoilage can will still cost you money. In this example, it's about 6 cents per can, which is the cost of aluminum, which is the cost of indirect materials, labor, and utilities. Now, luckily for us, that spoilage can be recycled and we can recoup some of that money. But the recycle value is less than a cost of the can that it took to make that spoilage. In this example, it's 2 cents, and the overall cost of spoilage is about 4 cents per can. Now, if we take that in comparison to the benefit of production, now let's say you do what you're supposed to do and convert that coil into sellable cans. The cost of each can is still going to cost you about 6 cents. But now that is completely offset by the sale price of that can. In this example, it's 10 cents. And this is the whole goal, is to sell cans for more than they cost to make. And in this example, you're making about 4 cents per can. So when you look at the total impact of spoilage, we take a production can, which could have a sale value of 4 cents, and we turn that into spoilage, which is actually costing you 4 cents. So the total impact is from one side to the other. It's 8 cents per can, and it swings either way, whether it's from spoilage to production or production to spoilage. So let's put some numbers behind this. Let's say your can plant has a spoilage rate of 6%. That is about 70 million cans a year, which is about 8,600 pallets of cans that could be worth $2.8 million worth of gross profit. And if we destroy that and turn that into spoilage, that's about 70 million cans of spoilage that is costing you $2.8 million. So that is a total impact of about $5.6 million of spoilage. It's huge. Think about that. So how do we address spoilage? First, it's important to create a culture of accountability. And culture starts at the very top, at the plant manager and the rest of the management level. On a regular basis, they should be walking the can plant floor and making it obvious to everybody that spoilage is not acceptable and eliminating spoilage is a priority. Once that culture is set, it's a lot easier to empower machine operators to identify areas of high spoilage and want to fix them. And finally, we need to treat HFI with great respect. And I want to talk a bit more about HFI, which of course means held for inspection. So cans that are HFI end up making it past the last inspection system onto pallets of cans. And ideally, these defective cans are identified before they make it onto a pallet. Because if they're not, the defects, as we know, cannot ship to customers. And the problem is that because of a few defective cans, the lion's share, the majority of most HFI pallets are good cans, but they're all held in quarantine in HFI status. So HFI as a whole is considered spoilage, all the good cans and the bad, until they are sorted and the defective cans are eliminated. Now, traditionally, sorting HFI pallets is extremely difficult. It is slow, it is inaccurate, and it is labor intensive. And so on a regular basis, most good cans that are quarantined in HFI are not sorted. So an HFI of 3% on an annual basis could mean up to 35 million cans. And that's just for a single can line. So think of the waste of scrapping all of these good cans. First, we'll look at this from a financial perspective. It's lost opportunity. So those 35 million HFI cans, let's take a conservative number and say 50% of those are good unsorted cans that are for whatever reason making it into scrap, whether they're simply not inspected or they are not inspected efficiently enough with manual systems. That could leave 17.5 million good cans. And as we've already talked about, the opportunity from swinging something from spoilage to production is 8 cents per can. That is $1.4 million that is left on the table for scrapping these good cans. And that's for a single line. That hurts a can plant. That is not okay. Now, on the other side of these things, think of the waste of resources that HFI leads to. Those same 35 million cans, with 50% of them being good and unsorted currently, results in 17.5 million cans that are scrapped. And every single one of those cans requires significant resources to make. This is water. This is gas. This is electricity. And if these good cans are turned into spoilage as opposed to recovered and sold, all of those resources were used for nothing. And that hurts. That hurts the can plant, that hurts our industry, and it should not be acceptable. And this is why IPS has come up with the Rapid Sort system. The Rapid Sort is an offline HFI inspection system that uses high-speed conveyance and vision inspection systems. And I'd like to show you how it works. First, the HFI pallets are loaded into the depalletizer, and layer by layer they are swept onto the accumulation bed, where cans travel in mass over to the single filer. And at the single filer, this is where cans begin moving fast. And once the high-speed inspection begins, this is where we use vision inspection cameras. We use the two major makes and models for our industry to identify things like deco defects. We can look inside of the can. We can also identify, for example, ink dots at the bottom of the can. If, for example, an IC spray machine led to metal exposure. And the whole point is that bad cans are identified and then they are rejected. And once these bad cans are rejected, the good cans continue on, and eventually they are palletized, and we are going to make that giant opportunity swing from spoilage to production. So this is the IPS Rapid Sort System, and we have ROI calculators that we can take your can plant's numbers and tell you how quickly you can recoup your investment and start turning your spoilage into sellable cans. And finally, I want to talk to you a bit about a brand new product that we have at IPS. This product is called the Airsave, and it is a valve system that we're currently testing on body makers to control the strip air. So this is a body maker, and we all understand that the purpose of the body maker is to turn cups into cans. And at the end of the stroke, it is important that that can gets stripped off of the punch. So right around the time where the punch hits the domer, strip air turns on. And this is an image of what strip air looks like. So the purpose of strip air is twofold. One, the compressed air enters the can so that it does not collapse under the pressure of vacuum. And secondly, the strip air helps in actually pushing that can off of the punch. So we are extremely happy to share some preliminary results with you guys. We have a body maker that we've been testing for a number of months in the United States. And from a sustainability perspective, we are seeing compressed air savings from between 58 to 78%. And this is in comparison to the two competitive valves, which would be solenoid valves, such as a MAC valve or a rotary valve. And the cost savings, because compressed air costs money, can be between $2,500 to $6,500 a year per body maker. And as energy prices increase, this will only go up. And finally, there's longevity and performance data, where MAC valves, the solenoid valves, may be changed out every 3 to 4 months on every body maker. The Airsave valve is expected to last at least 2 years. And if all of this wasn't good enough, the sustainability, the cost savings, and the longevity, in our preliminary findings, we are seeing that the Airsave system is actually helping improve performance of the strip air, actually allowing for more uptime of the body makers and fewer tear-offs. Currently, we are testing for the major body makers in the United States, and towards the end of the fourth quarter and the beginning of the first quarter, we will be ready to sell the Airsave valves to body makers around the world. So today we've covered a lot. First off, I want to share that all of the animations in this presentation were created by the Can School team at IPS. Secondly, we talked about the Rapid Sort system, and if you're interested in seeing the ROI calculator, please contact us. And finally, we shared information about the Airsave system, a better body maker strip air valve system. Thank you very much.